Good morning and thank you for joining us. Today's webinar is on the validation of US EPA method 524.2 with the Lumin Purge and Trap Concentrator. We will be taking questions at the end of the webinar, so feel free to submit those throughout the presentation. All right, Roger, go ahead.
Thank you, Shelley. Welcome to today's webinar on the Lumin Purge and Trap Concentrator, our Tekmar's newest Purge and Trap Concentrator. I'm Roger Bargesley, an applications chemist here at Teledyne Tekmar. Welcome. What we're going to be talking about today is the Lumin Purge and Trap Concentrator. We're going to talk a little bit about the concentrator first. Then we're going to have one of three questions for you, and that's the current purge and trap methods that you may be using. Then we're going to talk about the water management of the Lumin itself. This was specifically designed for a moisture control system to reduce the amount of water being put onto the mass spec systems. Then we'll go over the Lumin data that we used to validate US EPA 524.2 with this method. The Lumin Purge and Trap Concentrator now has USB connectivity so that it connects to modern computers. No more RS-232 connections, so you can plug it into almost any computer out there on the market nowadays. It can be used as standalone for a single analysis, just like the Stratum. It also can be automated with an autosampler similar to the Aquatech 100. It has a simplified trap replacement versus the Stratum. We also developed it to have an improved moisture control management system with the modern moisture control system. So now the dry purging is actually optional. We also made the trap cool down a lot faster so that you don't have to wait for the trap to cool down like we did in the Stratum. But we still have the mass flow controller for accurate delivery of helium and nitrogen. Also, we still have what was available on the Stratum. We still have a sample heater that you can put on the Sparger. We still have the Guardian foam sensor, so if a sample foams, it'll stop the analysis. Or the Guardian with the eliminator that will stop the analysis, add some defoamer so you can continue on with it. And also, if necessary, you can read the sample pH when using the Aquatech 100. Talk a little bit about the quicker trap change capability of the Lumin. Unlike the Stratum, where you had to open up the top cover, take off the valve oven cover, and expose the hot valve oven to your hands and things, all you have to do here on the Lumin is open the access door. With this little tab here, you can see the trap right there. No more condensate trap. You use a wrench to disconnect the 3/8 inch permanent nut here on the trap and a 7/16 inch wrench to disconnect this nut up here. Very few heated zones. Slide out that trap and put in the new trap and reconnect it. You don't have to cool off the hot zones anymore to avoid burning your hands. Also, easier access to the valve board so you can do testing if you need to when you're doing troubleshooting. First question we want to ask on the poll is, what is the current purge and trap method that you are using in your laboratory? So if you take a few minutes to go ahead and vote on this poll and let us know what you guys are using out there so we can kind of focus on future articles we may want to, app notes that we want to publish to help you out and other people. Recently, we've had some international contacts where we worked with international companies on developing processes for theirs, so that's why we have the state and the non-EPA international question down there. If you could, if you have a specific question on one of these state methods or an international method, please send us a question and we'll try and answer those today or later on. Okay, for the results of the poll. Looks like a lot of people out there are using US EPA method 500 series. We thank you for your responses. Moving on. The first part we're going to talk about is the water. How much water does a Lumin truly take versus the Stratum out of the system? So we did a water evaluation comparing the two. The GC parameters here, you can see we used a typical environmental column 20 meter 0.18. Helium carrier, we upped the split ratio from 100 to 160 to 1 because, again, we're putting a lot of water on the system, so we wouldn't want to overload the mass spec detector. We increased the septum purge to 3 mils per minute from 0.5 that we would typically use. And then we changed the oven program a little bit to better quantitate the water that was coming off the lumen and the stratum. The mass spec parameters, we use a standard environmental setup. We do use a turbo pump instead of a diffusion pump. We scan from 18 to 150 mass units. This is so we could see the water. To do this, we reduced the multiplier voltage significantly so that we wouldn't overload the multiplier with too many ions. And then we set the solvent delay to 0.1 minutes, and I put the solvent delay in there in parentheses as it's really, to us, not a solvent delay, it's just a delay. We used the 25 mil Sparge Vessel versus a 5 mil Sparge Vessel because EPA 524.2 in section 6.2.1 says that that the purge device has to accept a 25 mil samples with a water column of at least 5 centimeters deep. A smaller 5 mil purge device is recommended if the GC-MS system has adequate sensitivity to obtain the method detection limits required. So this comes up to our second poll question that we'd like to ask. It's a true or false. True or false? 440 mils of dry gas, helium, will absorb significantly more water from a 25 mil Sparge vessel than a 5 mil Sparge vessel. So again, we want to see what people feel out there. Is this true or false? Are we going to put more water on with a larger Sparge vessel or less water on? We'll let the poll go for another few seconds here. Looks like everybody's voted. I appreciate that. I'm going to close the poll and now share that with you. And we'll move on to see the results. If the 25 mil versus a 5 mil chromatogram of just the water only, you can see here we looked at mass 18, which is the molecular weight of water. With the stratum, we didn't see a lot of difference. The peak area looks different, and that's some of the consistency that we don't have with the stratum. With the lumen, however, because we've used the moisture control system, we better control that moisture so we get a better overlay of the chromatogram. And as you can see, the 25 mil and the 5 mil Sparge vessels put approximately the same amount of water onto the mass spec system. With the stratum, graphing this, as you can see, the average peak area of 5 injections has almost the same. Oh, sorry. I was told I forgot to hide the poll, so let me go back. Back to the 25 versus 5 mil chromatogram. As you can see here, with the chromatograms, I want to point out again the amount of water put on here based on the abundance of the water. The stratum has consistency on that addition of water to the system, where the lumen with the moisture control system does a better job. Also looking, I forgot to point out that there is a drastic peak area difference here too. With the stratum, graphing this, again, the 5 injections, the average of that peak area, they're very close. With the lumen, again, there is not a very large difference between a 5 mil and 25 mil Sparge vessel. Something else we noticed when we did this was we also injected surrogates and internal standards typical for 524.2. With this, for most of them, we didn't see a significant difference between the 5 and the 25 mil Sparge vessel, except for the polar compounds like methanol, which we use to make up our internal standard with, and the MTBE, which are polar compounds. We think that this is because you're going through, instead of a 6 mil column of water, an 11 mil column or centimeter column of water, sorry, that's centimeter, and that these compounds have time to reabsorb back into the water and reach a better equilibrium with them. So that's why we possibly are seeing this. Moving on to the Lumin moisture control system, we see an approximate 50% reduction in water versus a stratum. But this is dry purge time dependent, and we'll go over some of that data here shortly. But let's first look at the comparison to chromatograms. This is with a 1 mil dry purge, 5 mil Sparge Vessel, and as you can see, the stratum has a lot more water than the Lumin puts on the system. So the moisture control system appears to be really reducing the amount of water. Graphing this data over a 0 dry purge time to a 3-minute dry purge time, as you can see, the stratum, as you dry purge, reduces the water, but even at 3 minutes, you still don't reach the level that the Lumin does at 0 minutes. For a facility that is running a lot of samples per day, this takes quite a few minutes off of your total runtime so you can process more samples per day. Looking at those numbers, again, remembering that we're comparing this per dry purge time. So we get a 55% water reduction over the stratum with the Lumin at 0 minutes, yet at 3 minutes we only see a 39% reduction. And again, the Lumin is being consistent in the way it handles the water. Let's also look at desorb time. This is part of the amount of water that goes onto the mass spec. Section 11.2.2 of 524.2 says that after the 11-minute purge, place the purge system in the desorb mode for about 4 minutes. 524.3 and 524.4 allow laboratories to change this parameter. What we did was we looked at water, and we also looked at 97 other compounds typical for 524.2, plus we included some ketones and other compounds like MTBE to help understand how the system works. As you can see with the Lumin and a 5 mil purge vessel, there's a significant reduction of water from 4 minutes down to a half minute. At 4 minutes, that water peak will spread out to approximately 5 minutes, where with a half mil desorb time, that water peak is gone within 2.5 minutes. Looking at this graphically and with the numbers, as you increase that desorb time, you do put a lot more water onto the system. If you take it as a percent of the 4 minutes, the half minute is 13% of that quantity of water. Or thinking another way of percent reductions, that's a 658 roughly percent reduction of water going onto the mass spec system. Now for our next poll. A longer trap desorb time is necessary to transfer more analytes to the column. True or false? And again, this is some things I've heard is that you have to have this longer desorb time to transfer more of the compounds and get more accurate numbers. It looks like everybody's taken the poll, so I'll go ahead and close that and share it this time. I apologize for the last time. As you can see, a lot of people feel that's false. So using standards, again with the 70-some or 90-some compounds, these are the GC parameters we use, which are typical for what we do with an EPA analysis, 100-to-1 split. Oops, I did it again. I forgot to hide it. I apologize. These are the GC parameters. I appreciate the help out there. Back to 100-to-1 split is typically what we use for standard analysis here. Oven program, step and purge we drop down. Standard temperature program. Here we went down to 20 mass units instead of 18 because we wanted to up the multiplier voltage but not overload it with the mass 18 ions. But yeah, with the 20 we can still see the water. And then we went up to 250. and again a solvent delay time of about 0.6 minutes. One thing we noticed is, as we saw before with the water, there is a disturbance out to about 5.5 minutes with a 4-minute desorb, and you can see that little drop of water in here. Also, there's a couple peaks that you notice that they start merging together versus a half-minute desorb. And you may think that these peaks, you're going to get poor data on it. However, with the mass spec, you're able to look at a specific ion and quantitate that, and methyl acrylate, which is one of the peaks that we were looking at, is also co-eluting with numerous other peaks at that 4-minute retention time. But as you can see here, you get a very good peak shape with the mass of 55, which is the quant ion for methyl acrylate. So what we did, we calculated all the data as a percent of the half-minute desorb peak. 97 of the compounds we looked at, we included the internal standards and surrogates that we had for this run. 93% of them had less than 20% difference from the 0.5-minute desorb peak. 4 of them we found had greater than 20% difference, and these were typically the polar compounds that are difficult to analyze anyway. Looking at that graphically, we included the fluorobenzene here as the internal standard for 524.2, and you can see a little drop as the goes on. But most of the first 6 gases, you don't see a lot of difference from that. Again, this was from 5 injections of a 5 ppb standard, and we took the average of those 5 injections for each data point. Moving on to the polars, as you can see, the polars do increase. They mimic similar to what water does, and they like to stick to the trap a little bit. However, even at 140%, 150% difference from a half-minute dry purge, the question I would have out there is this a significant number that the detection limit would be significantly lowered? Moving on, so what we did was take the lumen, set it up to around a calibration curve for 524.2. The purge parameters we used are 40 mils of helium for 11 minutes. We used the 5 mil Sparge Vessel. 1 minute dry purge is the default that the method in the lumen calls for or has in the procedure. We did a 4-minute desorb like 524.2 did, put a bunch of water on the system. We used the K-trap. Again, the typical parameters is this time we used it on a DV624 column. From 35 to 260, we bumped the multiplier up a little bit higher this time because we're moving back into the range where we're not going to overload the multiplier with ions that don't need to be there. Looking at the data, the calibration data, the response factor is from 0.5 to 50 ppb standard curve. So what we did was take the response factor for each data point, calculated as an internal standard versus fluorobenzene, and you can see the percent RSDs are well below the EPA maximum limit of 20%. All the MDLs are very low also. MTB as a surrogate was put into the same concentration of each sample, 12.5 ppbs. We got a 2% RSD on that, which is very good. T-butyl alcohol is in there at a 2.5 ppb because it's a hard to detect compound. Again, very low response or RSDs on that one also. Propionitrile is one that people have a hard time purging out of water unless you heat it up. For this procedure, we could see it from 1 ppb to 50 ppb, but because our MDL was done with a half ppb standard, 7 of them, we didn't calculate this data point. Fluorobenzene again was our internal standard for the calibration curve from 0.5 to 50, where the internal standard is in there at a constant concentration of 12.5 ppbs. Again, 2.8% RSD, very good RSDs on that. Same way with the surrogate, 1,4-difluorobenzene. Moving on this column, 1,1-dichloropropionone and 4-methyl-2-pentanone co-elute, so I had to use some different ions. They were also in there at a higher concentration. Again, these are more compounds that are difficult to purge out of water. Even with that, at the higher concentration, we were still able to get very good linearity on both these compounds and fairly low MDLs. Chlorobenzene, as you can see down at the bottom, is another surrogate. Moving on, VFB had a 4% RSD, which is really good. Very low MDLs. Next group of compounds, moving down the 524.2 list, 1,4-dichlorobenzene. And again, nitrobenzene was one we could only see from 2 ppb to 50 ppbs. The linearity for that curve was 1.7. Again, because we used a 0.5 ppb, we weren't able to calculate the MDL for this compound. So wrapping up the Lumin, today we talked about its moisture control system that was specifically designed with modern technology to save time, 50% water on the GCM aspect and the stratum. The dry purge is not required anymore. The faster trap does cool down faster than the stratum. And then we made a change to make the trap change a lot quicker with easier access and no heated zones to where you can burn your fingers. I'd like to thank you for your time today. I'll start taking questions.